Good afternoon. It's my pleasure to introduce our paper on target counting by sequential snapshots of binary proximity sensors. This is a joint work with Mr. Tongyang Li, Mr. Lei Song from Institute for Interdisciplinary Information Sciences, Tsinghua University. I'm also from this institute. And Dr. Hai Shengtan from Jinan University of Guangzhou, China. My talk mainly contains 4 parts. In the first part, I will introduce the background and the related work of this work. And in the second part, I will introduce the lower bound of dynamic target counting. And in the third part, I will introduce the upper bound derived for dynamic target counting by binary proximity sensors. And at last, I will introduce a condition for precisely target counting by binary proximity sensors. At first, I will introduce the background and the related work. Binary proximity sensors are actually abstract sensor model for a large range of sensors. A binary proximity sensor, which is shorted as BPS, outputs 1 when one or multiple targets are within its sensing range. Otherwise, it will output 0. Let's look at an example. There are 2 sensors in the sensing field. Each sensor is represented by a dot, and each sensor has a sensing radius. When there are targets within the sensing radius, the sensor will output 1. Otherwise, the sensor will output 0. We call the active sensors in on state and the inactive sensors in off state. And the sensors in off state will be represented in gray color. BPS is an abstract model extracted from many real-world sensors, including infrared sensor, microwave sensor, magnetic sensor, acoustic sensor, radio signal detection sensor, ultrasound wideband sensor, and millimeter wave radar. However, although binary proximity sensor is very simple, it is highly limited in target counting and target detection. At first, it cannot recognize the targets. It don't know who it is detecting. And it cannot distinguish one from multiple targets. And certainly, it cannot provide any direction nor location information about the targets. Let's look at another example. In this example, there are 2 cases. In both cases, there are 2 sensors. And in the first case, one sensor is detecting 1 target in its sensing radius. And in the second case, the sensor is detecting 5 targets in its sensing radius. But we can see that the output of the 2 sensors are totally identical. So the sensors cannot know how many targets is in the sensing field. This motivates the target counting problem, which is extremely important in the target counting and tracking problem using the binary proximity sensors, which is the foundation of the array. The target counting problem investigated in the paper, the model of the problem is like this. The input of the problem is a network of NBPS deployed in the area of interest. And the readings of these sensors from time 1 to time t are supposed given. We call them snapshots of these sensors, which is denoted by S1 to ST. where Si is a Lens binary vector indicating the states of sensors at time I. These are the inputs of the problem. And the output of the problem is to count the number of targets in the field. We consider the targets can move arbitrarily in the sensing field during this period, but we assume that the number of targets doesn't change in this short period. So the problem is to count the number of targets in this setting. There are some existing results which has investigated this problem. The first result is given by Singer in EWSN 2007. They investigated multiple target counting problem in one-dimensional space. They showed that if the on sensors could be partitioned into at most X positively independent sets, the number of targets in the sensing field is at least equal to the cardinality of X. Let's use an example to understand this theorem. In this example, there are two cases. Let's firstly understand what is the positively independent sensors. Two sensors are positively independent if their sensing radius don't have overlapped area. For example, in case 1, these two sensors are positively independent. The second case for positively independent is that although the two sensors have overlapped area, but the overlapped area is fully covered by the area of off sensors. So the on regions of the on sensors are positively independent. So the size of the positive independent set gave the lower bound of number of targets in one-dimensional space. In the same paper given by Singer in EWSN 2007, they also presented the precisely target counting condition. They show that the number of targets can be precisely counted when the minimum pairwise separation distance among targets is larger than 4R. This is easy to understand, because when the minimum pairwise separation distance among targets is larger than 4R, then all the sensors are positively independent. So the number of targets is equal to the size of the positively independent set. So the lower bound is equal to the real number of targets, so that the number of targets can be precisely counted. In our early result in 2014, in Mobile Hawk, we investigated the lower bound of target number in two-dimensional space. We investigated the problem by connecting the on sensors. After connecting the on sensors, we can treat a snapshot, the sensing model of sensors by a unit disk graph. As shown in this example, after we connecting the on sensors, the network model is a unit disk graph. Then we show that the lower bound of number of targets is equal to the minimum click partition of the unit disk graph formed by the on sensors. Let's look at this example. The sensors, the on sensors, have been partitioned into 3 isolated islands. This is the first isolated island. The isolated islands has the minimum click in this isolated islands is 1, and this is the second isolated island. The minimum click is also 1, and the third isolated island has the minimum click 3. So the sum number of sensors in the whole array is 1 plus 1 plus 3, which is equal to 5, given by the minimum click partition of the UDG formed by the on sensors. We prove this lower bound of target number is tight in the paper. From the previous result, we can see that all the existing results on the target number lower bound only investigate the target number by one snapshot. Can we further improve the target number lower bound? Let's look at this example. In this example, there are 4 sensors. At time t0, all sensors are in off states, and at time t1, sensor A is triggered on by one target when one target moves from outside into the sensing region of this sensor. And this arc, we call it a feasible crossing arc of the target. And at time t2, which is very close to time t1, when another target moves inside the sensing area of this sensor also turns into on state. So we can say that there should be 2 targets in trigger these 2 events, but the lower bound given by the minimum click partition is 1, because there is only 1 click formed by these 2 on sensors. So because the moving speed of the target is limited, the events at time t1 and t2 must be triggered by different targets. So the lower bound in the scenario should be 2, but the lower bound given by the MCP method is 1. Therefore, by jointly consider the sequential snapshots, it is possible to improve the target counting lower bound. This is the main motivation of this paper. Therefore, in this paper, we consider the dynamic counting problem by a sequence of snapshots. We consider the dynamic counting problem. The input is a sequence of snapshots. Without loss of generality, we assume T1 is less than T2 is less than Tn. We also assume the number of targets will not change during T1 to T2, Tn, and each target's movement speed is upper bounded by Vmax. And the desired output of the problem is the lower bound with consideration of spatial and temporal dependency between the snapshots. To investigate the problem, we firstly give an important definition, which is the feasible crossing arc. When censored states change happens, the feasible crossing arc indicates the arc where the targets may be traversing to trigger the event, without violating the states of other sensors. Based on the feasible crossing arc, we gave the following theorem, which is called the time-space restriction for target separation. If a sensor A is triggered on by one target at time Ta, and the feasible crossing arc is Fa, another sensor B is triggered on by the same target at time Tb larger than Ta, with feasible crossing arc Fb. Then, if the 2 events are triggered by the same target, then the following condition must be satisfied, that the distance between the 2 feasible crossing arc must be less than Tb minus Ta multiplied by Vmax, which means that the distance between the 2 feasible crossing arc must within the moving limitation of the target within the period, where Vmax is the maximum moving speed of target. Based on this theorem, we present a dynamic counting algorithm. The key idea is to delete the edge from UDG if the time-space restriction is not satisfied by one target. Using the same example as shown in the previous slides, these two events cannot be triggered by the same target, so we delete the edge between the two unsensors in the underlying UDG graph. By deleting this edge, the topology of the UDG is changed, and after deleting this edge, if we calculate the lower bound of the target by minimum click partition, we can find that the new lower bound is 2 instead of 1. So the dynamic counting method can improve the lower bound given by MCP method. And this slide shows the simulation result of which compares the static and the dynamic counting performances. In the evaluation, 100 sensors were deployed randomly in an array of 100 meters multiplied by 100 meters. 10 targets moves randomly in the array, and we consider the number of targets in this dashed square array. In the right-hand figure, the blue curves shows the real number of targets in the dashed array over time. And the red curve shows the dynamic counting result, the dynamic lower bound. And the blue curve shows the static lower bound given by MCP. We can see that the dynamic lower bound is better than the static lower bound. And this figure shows the relationship more clearly, that the dynamic lower bound can improve the static lower bound of up to 10%. So this is the improved lower bound for dynamic target counting. We also investigated the upper bound for target counting. Previously, there is no upper bound of target number given in the literature. But we can consider the real targets, such as human, animals, vehicles. They are generally not arbitrarily close to each other. If there is a minimum pairwise separation distance R between targets, an upper bound of a target number can be given by packing theorem. As shown in the following figure, if we know the on region of the on sensors, and we know the minimum pairwise separation distance between targets, then the upper bound of target is to find the maximum number of disks in the feasible array. So the packing theorem was given in field by 1910s. It established a theorem for the density of circles packing into a connected surface. Based on the packing theorem, we presented an upper bound for target counting. Let AI and CI be the array and the circumference of the S feasible element, respectively. Suppose the minimum separation distance between targets is R, then the number of targets in the feasible array must be smaller than this value. This is the upper bound for the number of targets. And we use an evaluation to show the performance of the upper bound. 20 is the ground truth in our evaluation. And when we increase the pairwise separation distance between targets, we can see that the upper bound is become closer to the ground truth. This is because in real applications, the targets are generally very sparse, and the pairwise separation distance between targets is generally large. So we can increase the pairwise separation distance to improve our estimation to the upper bound of the target. At last, we investigated the minimum separation distance for precisely target counting. As I mentioned, the previously best known pairwise separation distance for precisely target counting is 4R. And in our paper, since we know the lower bound and the upper bound, when the lower bound equal to the upper bound, we can precisely count the number of targets. Based on this, we derived the the condition for precisely target counting. The minimum required separation distance between each pair of target for precisely counting is R, given in this value. And let's look at an example to understand this theorem. In a snapshot shown in this figure, we can see that the pairwise separation distance between two targets, if the pairwise separation distance between the two targets is larger than 33, then the number of targets must be precisely counted. So the new pairwise separation distance is less than 4R. And by simulation, we show that the new pairwise separation distance can be reduced by 17% than 4R. In this figure, 8 is 4R separation distance, which is the previous minimum separation distance. In the simulation, R is set to 2, so 8 is equal to 4R. And by our method, we can see that when the pairwise separation distance is less than 4R, the number of targets can also be precisely counted. And it improves the previous condition a lot. So in conclusion, we present the time-space restriction to utilize a sequence of snapshots to present a new lower bound for target counting. The packing theorem was employed to design a new upper bound for target counting, and a new minimum separation distance for precisely target counting was derived by above lower bound and upper bound. That's all. Thank you for your attention, and we are online for your questions. Thank you very much.